Now, I'm going to give an introduction about the ant colony optimization. When we talk about ant colony optimization, it is a kind of swarm intelligence. Now, when we compare the genetic algorithm, the evolution strategy, all of them based on the Darwin evolution theory. But now, when we talk about the swarm intelligence, it means that we are talking about a group of agents, a simple agent. They work together to find out the solution. For example, we have a few figures right here. We have some ants, and then this is the last. They want to find the food. In the middle, we have the obstacles. That means we have different paths to use. For example, starting from A and then go to B and then D and then find the food. Or we could have a longer path, A, C, and D, and find the food. So, how come the ants they're able to finally find out that this is the shortest path, and then most of the ants they use the shortest path, because they cannot talk, and then they can have only local information. How do they communicate? So that everyone work together to find the shortest path. That is a kind of swarm intelligence. So in the literature, we have different definition of the swarm intelligence, but actually they refer to the same thing. When we talk about the swarm intelligence, and then it is a property, the property of a system. The most important thing, that is the collective behavior, of unsophisticated agent. That means ants. They are the agents. They are simple agent. They work together. That means this is the collective behavior, and then so that they are going to interact with each other locally, because these ants can communicate with these group of ants, and then so that to tell the environment, the landscape of this environment, so that they come up with the global solution, the shortest path. So that means work together to emerge the global solution, and then that is the swarm intelligence. Another one, swarm intelligence, that is to explore collective problem or distributed problem. That is the same collective behavior, and then it points out another thing, that is without centralized control or a global model. That is, no one is going to tell what each ant is going to do. They are going to act by their own, and then they are going to communicate with each other, and they are going to find out the global solution together. So example, rather than the ants, and then we can find out that a group of fishes swim in the same direction, and then this is a swarm intelligence. How do they communicate so that they are not going to crash with each other and then swim in the direction? Okay, and now take a look at a little bit more about the characteristic of the swarm intelligence, and then because all these characteristics, they are very useful for us to develop some algorithms to perform the learning. The first one, that is the flexible. It means that no matter how many ants we are going to use, how many agents we are going to use, as well as no matter the change of the environment, and then these agents can solve the problem. For example, this time we are going to use this is the last, and then this is the foot. Whether we have an obstacle right here, this time we only have 2, and then the next time we have 3, and then these ants can find the shortest path. And then next time we may have an obstacle right here, or the foot source that is changed to another direction or location, or sometimes we are going to send a group of ants that is 100. Next time we have 200, and then so this is the internal interpretation as well as the external challenges, and then these agents can also solve the problem. So this is the flexibility that is important for us to have a learning algorithm can deal with different kind of optimization problem. Yeah, and then robust. That is, think about that. In the process of finding this food source, suddenly some ants they get lost. From 100 reduced to 80 or reduced to 50, and then so the task can be completed as well. Yeah, decentralized. As I mentioned before, all these ants they act individually. We do not have a model. We do not have a leader to tell them what to do. Yeah, so this is another property, self-organized. That means this solution, when we find this solution, we have a mechanism to find the global solution. We do not have a predefined solution right here. You can imagine that when this environment change, the food source is right here. We have different obstacles, and then the ant can still use the same learning mechanism to find the shortest path to the food source. Yeah, okay. So later on, we will appreciate the ant colony optimization will have these characteristics. Now I'm going to focus on the self-organization. What kind of ingredient we have to use to implement the self-organization? If we are able to figure out that, and then we are able to implement that, yeah, in an algorithm. Yeah, so this self-organization, it is a kind of dynamic mechanism, so that the structure, yeah, so the structure appear at the global level. It means that we are going to emerge this global solution. Yeah, emerge the global solution through the interaction of the agent. Yes, the low level component. It means that that is the interaction of the of the simple agent. They are the ants. 4 basic ingredients. The first one, positive feedback. That means when we have some ants from the left, some obstacle in the middle, the food source right here. So when we send out the ant, we can have this way, we can have this path, we can have this one. How do we indicate that which path is shorter? If we find out that this is a shorter path, and then we have to do the positive feedback to amplify that this one is a better path. Yeah, so this is the positive feedback, and I will let you know how do we perform the positive feedback later when we know further about the ant colony optimization. Negative feedback, yeah, so this is something we have to implement. Otherwise, if we just simply randomly pick a path and find out that this is the best path at the moment, if we are going to reinforce that too much, and then that will become premature convergence. It means that this may be the best path at the moment, but it may not be the best path globally. Yeah, so we need to introduce some negative feedback to each path to reduce the effect of positive feedback. Yeah, so that the thing we would like to do is that to ask some other ants to explore some other unseen path. Yeah, so this is the amplification of fluctuation. So we are going to introduce randomness or error. That means we accept error. So that means even though this is the best path we find, we still send out some ant in different direction in order to explore the area. Yeah, so this is the randomness, so that to find a better path. And then multiple interaction. Yeah, so this one, that is, once we have many ants in this environment, how do we communicate? How do we send this information to other ants? Yeah, so that we come up with the shortest path, and then all these ingredients we have to implement that in the ant colony optimization, so that we are able to find the optimal solution. So why ants? This is the motivation. From observation, we can just find out that ants appear on the earth some 100 million years ago. That is much earlier than human. Yeah, and they can still survive up to now. That means they have the mechanism to survive. If their solution is not optimal, they cannot survive for so long. Yeah, and the population size, that is in total in the Earth, 10 to the 16 individuals, that is a very large amount. And also when we consider the colonies, that is from 30 to millions, that means this kind of mechanism works for 30, a small population, or to millions of population. So it is very flexible. Yeah, collective behavior, they have their own way to work together. And then this is the most important thing. We need to learn this behavior so that we are able to transfer this knowledge into a mechanism, a computer mechanism, that is the learning algorithm we are going to learn today. Yeah, all this agent very easy to implement because it is stimulus response, a very simple agent. That means when we interact with the environment, what is in the environment, we will have a direct response from the agent. Yeah, so they do not have much intelligence individually, and so that's why just some simple and basic action for each agent, so it is very easy to implement. Yeah, okay. Also, they have a very large random component or mechanism when they work together. So when we look at all the ant colony, actually we figure out these basic ingredient, yeah, as well as these kind of property. So that's why ant is a good example for us to learn from, observing how they work together, and then so we can just simply transfer their skills, their mechanism into a computer learning algorithm, that is the ant colony optimization. So what an ant optimization algorithm can do. So this is the problem, a general problem, that is we are going to find the optimal path in a graph, that is to find the shortest path. Yeah, because we do minimization, of course you can find the longest path, but anyway, by default we are going to find the shortest path. So we can have the application that we specify. Loop 1, that is the last, that is the source, the source point, the starting point, and then 7, that is the foot source, that is the destination. Okay, so that means we are going to find out the path from loop 1 and then our target, that is 7. Yeah. Okay, so this is one way of the formulation. If you are able to formulate the optimization problem into, for example, a graph, and then we can apply the ant colony optimization. Okay. So again, in some other applications, we do not specify a fixed loop to be the source or a fixed loop to be the destination. Yeah. So in some cases, we can, in different iteration, the source and the target can be changed. Yeah. Okay. This is the notation we are going to use. I'm not going to go through each one, and then in the due course, I'm going to introduce the symbol to you. Okay. Now, this is as I mentioned before, that ant is a good example for us to learn the mechanism. So the first thing, that is, we need to learn how do they find the shortest path, and then as well as how do they communicate. Yeah. So this one, we call this is the binary bridge experiments. Yeah. So given right here, this experiment is something described by this figure. That means we have elapsed the starting point, the foot, that is the target point. So we are going to send some ant using different way to find the path and find the foot source. And now, in this experiment, the lower bunch and the upper bunch, they are of the same length. And then, but we find out something that is very interesting. This is this figure. X-axis, that is the time. Y-axis, that is the number of ants using upper and lower bunch. Okay, so in the beginning, right here. So that means they distribute evenly, so the same number of ends. So in the beginning, the same number of ends using the upper and the lower bunch, and then suddenly at this point, the lower, this one, this is the lower bunch. Square is the lower bunch. This right here, a few more ends using the lower bunch. It indicates that the less end, fewer ends, they are going to use the upper bunch, indicated by dot. And when time passes by, and one of the path, that is the upper bunch, become dominant, and then we still have some end using the lower bunch, but majority of them using the upper bunch. Yeah. So this one, because these two paths, they are of the same length, and then how come most of the end will use the upper bunch? There must be something happen in the group so that they know that this is the path they have to use. Yeah. Okay. Through this experiment as well as some study, and we've just find out that ants actually they deposit some chemical pheromone while walking. That means when they walk through this bunch, they are going to leave some chemical on the ground, on the floor, so that this is a kind of communication between ants. And then so if the concentration is higher, I mean the pheromone concentration is higher, and then it will attract more ants to use that path. Yeah, but they still have some randomness. That means some ants will ignore the concentration. They just randomly pick a path. So that's why even though majority of the ants they use this path, but we still have some small number of ants they use the lower path. That is the thing I mentioned before. This is the exploitation and exploration. Yeah. Okay. So the randomness. And now to build up a model, that is to tell you this model, that is to model how the ant picked the path, which path. Yeah. Okay. So assume that we have two paths. One we call A, another one we call B. Yeah. So PAT plus 1, that means the current time, that is T. In the next time, which the probability of choosing A, the path A, that is according to this formula. That means because we only have two paths, if we do not choose A, that means we are going to choose path B. So we can just say that PA equals 1 minus PB, because the sum of the probability is 1. Yeah. So NA and B, number of ends of path A and B respectively. So that means we are going to count the end in the path A, count the end of path B using path B. And now C, that is a value, a positive value, that is degree of attraction of an unexplored bunch. So in the beginning at this point, for example, when no n is using this path, that means all NA and B they are 0. So C divided by 2C, that is 50%. That means both paths will have equal chance to be chosen by an ant. Yeah. But when the ant they are increasing in A or B, and then this probability is changing. Yeah. So the alpha right here, so that is the bias. So that is something to do with the pheromone deposit on the path. So for example, the higher the concentration, the larger the value of alpha. The larger the value of alpha, and then this value will become bigger. So the probability of choosing A will be higher. Yeah. So that means this is a kind of amplification. So this is a simple model of modeling how an ant they choose the path. Yeah. Okay. Now that is, if we have an ant that is right here, we have two paths, and then this is the probability of A, probability of B, and then so what we need to do is to create a model like this, and then so once we calculate the probability, we are going to arbitrary a random number r, if r that is less than pa, we are going to use this path. Otherwise, we are going to use pb. So that means if pa is larger, and then there would have a higher chance to use path A. Yeah. Okay, so this is a very simple model, and now I'm going to explain a little bit more about how do the ants they are going to use these. How do they choose the shortest path? Say we have two paths. This is shorter. This is longer, and then this is the starting point, this is the destination point, and then when we perform the experiment, we just find out that most of the ants will choose the shortest path right here, and then so this is so this animation, this a video clip just so how an ant what the ant is going to do. So for example, at this point, randomly pick a path, and then this ant they're going to explore what is happening in this environment. The blue thing right here, this is the chemical, the pheromone concentration left by the ant. So you can see that when the ant find out that there's a trace of pheromone concentration, and then they are going to use that, attract the ant, use that. But now when the ant, because this is a path that is shorter, and then when the first ant go to this point, find the food source, and then this ant will go back to the last quicker than those ants using this path. And then that means next time this concentration will become higher and higher when more ant is using this path, and then because this is longer, and so the concentration will be lower in that case. Yeah. So we can also look at the next slide, which gives you another example, a very similar example. A longer path, shorter path. Both ants they are going to use one of the path, and then when they reach the food source, this ant assume that they use the same path to go back, and then the ant will leave the pheromone concentration when it goes back to indicate that this ant find the food. So now because this path is longer, and then this concentrate right here, we still do not find any trace of the pheromone right here, and then the third ant is going to decide which path it is going to use, because of this one has pheromone, this one does not have. So the ant will have a high chance to use this path. Okay, so if we are going to repeat this process, and then the ant go back using the same path, this concentration, the green stuff, will become higher and higher, the concentration. That means compare with this one, yeah, because this one takes longer time. That means the pheromone's concentration will not be as high as this one. Yeah, so later on this one become higher, and more ants will be attracted to use this path. And also remember one thing, that the pheromone will evaporate. That means that is the negative feedback. The negative feedback, that is, we reduce the concentration. On one hand, this ant will increase the concentration of the pheromone. That is the positive feedback to tell this is good direction. And then when time goes by, the pheromone concentration will be reduced, will be evaporate. That is a negative feedback. So that means this one will become higher. So more ants will be attracted to use this path. And then this figure indicate all ants they are using this path. It may not be very correct because some randomness, and then some ants will still use this longer path later on. Yeah.